Good evening, Year 12. Welcome to today's online learning session for AS Chemistry. Sorry about the little bit of delay there. We had a slight technical issue. So today's session will be delivered by Mrs. Stevens. She's an examiner for the WJC, so you're in good hands. In today's session, you'll be viewing reversible reaction, equilibria, and applying the Chatellier's principle. I'll now pass you over to Mrs. Stevens.
Good evening, Year 12. Apologies, you'll be able to hear my voice, but unfortunately, as Mr. Black said there, we've had a few technical issues, which is you can't see me, but trust me, that's no great loss, okay? So if I start from the very beginning then, this is probably one of the most challenging topics that my Year 12 this year have experienced. Partly for two things. I've had a mix of double award and triple award students coming into Year 12 this year. Now, this topic isn't even touched upon in the double award, as I'm sure you're aware. And even if it is touched upon, as it is in triple award, it did unfortunately fall at the later end of Year 11. So quite a few of my Year 11s hadn't experienced any sort of input on this due to the fact that the pandemic hit when it did. So it's a relatively new, fresh topic for quite a few pupils, I'm sure. So I'm hoping just to go through the basics with you and just build a bit of confidence and hopefully strengthen your understanding of this. But hopefully by the end of the session will be a relatively straightforward concept to you. Okay, so as outlined in the specification, it is topic 1.7. Now, I'm going to concentrate primarily on the initial few learning outcomes there. So the reversible and what the word reversible means in that sense. Okay, and also apply it then and build upon that to develop your understanding of Le Chatelier's principle. Okay, and then using that principle to decide what sort of effects would be seen if a system was exposed to certain changes. So hopefully by the end of this, what I hope to achieve is that at least all of you can define and state Le Chatelier's principle. And it's important as an examiner that you appreciate that there is no word perfect definition that we as examiners look for, but it has to be something that you're comfortable in regurgitating. So something you're happy being able to define using your own vocabulary. Okay, Year 12, that's really important that you fall into this zone where you're comfortable with what you're doing yourself. Okay, so reversible, as I said, is touched upon in the triple award part of the GCSE courses, but I'm sure it is a relative weakness with the majority of you if you didn't study it in real terms, that it was taught maybe remotely as my Year 11 were taught it last year. Okay, so during GCSE, we tend to shy away also from the fact that we say, I suppose, that most chemical reactions are not reversible. So we tend to kind of put you into this kind of mentality that if a chemical reaction occurs, then something new, magic is being created, and as a result you can't undo that process. Well, we know by now, or hopefully you know by now, that that's not actually accurate, and we are aware that some can go back from the products and reform the reagents. So starting from Year 7 onwards, we've said that things aren't reversible. So how do you describe between a physical and a chemical change? Well, simplistically said as if you're going to undo it, it's a physical change like melting chocolate. And if you can't reverse it, for example, I tell my kids, try untoasting a piece of bread, then it's a chemical change. So burning is classically the one that we know is not reversible, or is understood to be very difficult to reverse at least. So it's almost impossible to return to carbon dioxide and water, so return them to the original methane and oxygen. But we know that reversible reactions are more common than maybe people think. So we know that the Haber process we are meant to be familiar with from Key Stage 4, the making of ammonia, is reversible. Okay, so we can say on the screen there, you can see that there is a classic reaction where you have cobalt chloride and it can be transferred between these two colors, so that if it is a hydrated version, then it appears pink. So you can see that it would be pink to the site, So you'd look for a color that would be pink, but it can also, appear blue. Okay, so depending on those conditions, you can make certain colors appear. So if you want it to be blue, you can manipulate the system to kind of prioritize maybe the right-hand side of that equation, which is the blue coloration. So if you wanted, let's say you wanted blue, and just to recap, this side is pink. Okay, if you wanted to prioritize one side versus the other, then there is a way of doing that, because the system is always in equilibrium. Okay, so if you want it to be prioritized on one side, then you would change or tweak, should we say, maybe the pressure or the temperature, etc. Okay, so what is equilibrium? So reversible reactions reach a balance point. Okay, so where at the very beginning of any chemical reactions, you've got lots and lots of reagent particles, and they will collide and start forming the product particles. Okay, but there will be a point within a reversible reaction where once you've started taking those reagent product particles and created a few of the product particles, then some of those particles that you've made as a product will start reacting and reform the reagents you initially started with. Okay, so reversible reactions reach that balance point eventually, where you've got two reactions taking place at the same time, but in opposite directions. So we call this a position of equilibrium. So in general, if you take a generic equation, and I usually find it better to start with just A and B and going to C and D to just get it clear in your heads. Okay, if you start with A and B, at the very beginning, there is no product particles. So there's no C and D at the beginning. Okay, but once A and B start doing their magic and start reacting, you will get a few particles of C and D formed, and they will then be able to reverse and react with each other to recreate the initial A and B. Okay, so it reaches this balanced state by starting to react in both directions. Okay, so at the beginning, there is loads and loads. There's a really high concentration of A and B. They're at their maximum. Okay, because you got the most particles presence of A and B at the beginning, it also, just to cross-link in with the unit that hopefully you've either completed or you're touched upon in Unit 2 of Year 12, which is the rates equation. What you will learn this evening as well is that they often contradict each other. It's one of the kind of painful things about chemistry, is that you've got a certain strand of chemistry that inform you that this should happen, but then you've got another strand of chemistry that contradicts that. Okay, so we know, if we link it to the rates, that the reaction is fastest always at the very beginning of any chemical reaction. And that's, if you think about it, you've got loads and loads of A and B at the beginning and no C and D. Okay, so the products. So those collisions that we learned about in Key Stage 4 that are required for any reaction to happen is always going to be more frequent. So the collision frequency is massive at the beginning, because that's where you've got the maximum possible resource or stock of particles to collide with each other. So the rate is always fastest at the very beginning. Okay, so as A and B react, their concentrations gradually fall as they're being used up, and that means that they are less likely to collide and react. And so the rate of the forward reaction falls as any time proceeds. So as time goes on, the forward reaction starts to slow down because you're running out, in a sense, of reagent particles. Okay, in the beginning, though, we know that there's no product, so there's no C and D. So there can't be any reaction occurring between C and D because there isn't any. So the lack of any C and D means that the rate of the reverse reaction is at its lowest at the beginning, because there is no massive stock of product particles to collide with each other to react. But as time goes on, the concentration slowly builds up as A and B is being changed into C and D. And as more C and D particles are created, the collisions between them also start to speed up, because the frequency of collisions is also at its greatest. So with time, the rate of the reaction between C and D will increase because there's more and more C and D present to collide. What eventually happens then is that the two reactions become equal. Okay, so as A and B is being transferred or converted into C and D is at the same speed or at the same time being converted straight back into A and B. Okay, so you can see from that graph that you have this kind of plateau point where they are equal in a sense. So at this point, there won't be any further change in the amounts of A, B, C, or D. Now let's get rid of a very common misconception or a mistake that commonly is seen in exam papers, especially in year 12, is that pupils mistakenly possibly say there's no reaction occurring. And you can't be further from the truth at that point. The reaction doesn't stop. Okay, it's just that the two reactions are happening at exactly the same rate, which means that there's no visible change in concentration, because as soon as you get a certain component or proportion changed into the products, they will then reverse themselves at the same pace into the reagents. So it might mistakenly initially look like there's no reaction taking place. So as fast as something is being removed, it is being replaced again by the reverse reaction. So it's called a dynamic equilibrium. Now this is one, okay, of the key things you have to be able to define. It's one of the kind of, let's say, kind of staple questions that examiners will go for. Bear with me for a second. Okay, so it's one of the, as I said, key things that the examiners like pupils to be able to define. Oh, it doesn't like doing it. Right. So there is no perfect word for word. So I'll repeat again. You don't need to use the one that you see on screen there. You might have your own one that you're happier in recalling, that uses more common vocabulary to you, or words that you're more familiar with using. Find your own comfort zone, okay? As long as it says what it's meant to say, as long as the meaning is clear and you're not using any ambiguous vocabulary, then knock yourself out. Use whatever definition you are happy with, okay? Year 12, it's really important that you find your little comfort zone of definitions. So dynamic equilibrium there is, in my opinion, or my definition, then the point at which the forward and backward reactions continue at equal rates, so the concentration of reactants and products does not change. Okay, so on a molecular scale there is continuous change though, so you have to be clear that there is a change of molecules, it's just that it doesn't appear so. So it's the difference between what we call molecular scale and macroscopic scale. So visually there is nothing appearing, or nothing appears to be changing or happening. Okay, so be very careful not to think that dynamic equilibrium suggests that the reaction has stopped. Okay, year 12, it's still continuing, it's still happening at a great pace. Now this slide I'm going to just quickly brush over relatively quickly. It's just two quick clips that I found that demonstrate what dynamic equilibrium may look like to you, but also more importantly how that equilibrium can be shifted by a change in conditions. So the first one there shows you when you click on it, and as is the case with all of these Caralam sessions, okay, you will be given access to the PowerPoint that you're currently looking at. It will be provided to you after this session comes to a close, okay? So when you have it and you have the time and the willingness to look at it, I fully appreciate that lots of you have been in front of a screen for a massive proportion of your day already, so I appreciate you turning up at all. So when you have the time, look at these clips. It just shows you the different colors for a certain reaction taking place. So the two colors in the first reaction there goes from being brown to being near colorless, and depending on the temperature, so in ice cold it's a relatively pale solution of brown, and in hot conditions it's much darker. It shows you by a simple shift of temperature, nothing else, there is a visible change in what's happening. Okay, Right, now I'm going to stop and briefly, okay, just bring up a few questions for you, okay, and just breathe for a second, partly because I want to check whether there have been any sort of questions that have come into the Q&A, which, if you're not aware of, is always open to you throughout these sessions. So feel free to type into the Q&A, and my lovely colleague you heard at the beginning will, I'm sure, answer them promptly because he's far more capable than me. But just a quick pause just to kind of see whether you've kind of understood what's gone on so far. And if you're watching a recording, then literally maybe physically pause the clip and just take a look at these questions. So are you all happy that you could draw the symbol that shows reversible? So it's, if you remember correctly, this symbol, which shows you that you've got a reaction going in both directions, okay? Example reaction that's not reversible, something like combustion is the standard one. Example that is reversible, well, you've got two that you carry through from GCSE if you did triple award, which is the contact process of sulfur dioxide into trioxide, and then the formation of ammonia from hydrogen and nitrogen. So take a pick. I'm an avid fan of not crowding your brain with things that aren't necessary. Okay, you could learn endless examples. Why bother? Okay, as a teacher, I tell my pupils to use every bit of information they have for as many purposes as they possibly can. So if you can use one fact and apply it to 2 or 3 different bits of the syllabus, then please do so. Okay, there's no sense in overcrowding your brain with too much information. Right, and as I said earlier, it is really important that you have this definition of dynamic equilibrium. Okay, so it is a case of having a clear-cut definition you're happy with and then being able to regurgitate it to an examiner if asked to do so. Okay, right, so moving on, position of equilibrium. Okay, it doesn't always lie smack bang in the middle. Okay, so position of equilibrium, often what we call favours either the forward reaction or the reverse reaction. Okay, so it's a case of does it make more products or does it make more reactants? So we're moving in to discuss a key word here which is yield. Okay, so how much product you will get out of a reaction. Okay, so equilibrium, as I said, can lie either side, left or right. So meaning that once equilibrium has been reached, there could be more products or more reactants comparable to each other. The things that kind of affect this then, okay, so you might want to affect the amount of product to get as much as you possibly can, but you want as much as you can for as little money as you can in industry. So it's economics driven, I suppose. So if you can get lots and lots of it by manipulating the conditions, then industry tends to do so. Okay, so manipulating equilibria. Carbon dioxide dissolves in water. Once equilibrium has been reached, you can see no change in the gas bubbles in that container. However, if you notice here, okay, that is what I'm hoping now you are familiar with calling a proton. Okay, so H+ ion. If you add H+ ion though, what you will notice, okay, is that suddenly you'll get more bubbles created. And the reason you'll get more bubbles created when you introduce acidic conditions is because if you shove in more of this, the Chatelier's principle, which I'm moving on to, tells you that it wants to undo that. It doesn't want any more H+ or protons present. And the best way of getting rid of that is by using them up and making the reaction go that way, to the left-hand side. Okay, so if you introduce something, any reversible reactions tries to undo that change. Okay, tries to undo what you've done to it to make it go back to its kind of status quo, I suppose. So its state of equilibrium where everything was happy and balanced. So if you introduce something, it shifts or changes to undo that. Okay, now the specification specifically tells you that you must be able to demonstrate and apply that knowledge. And it's underneath that statement of Le Chatelier. Okay, so Le Chatelier's principle has to be used in deducing what effect temp, conc, and pressure will have on a system. Now, again, find a definition that you're happy with, okay? This is mine, and this is the one that year 12 that I teach are given. However, my best pupils always take my definitions and they change it into their own because they're happier to produce that definition in exam conditions. So in simplistic terms, I try making it as simple as I possibly can. Le Chatelier's principle was, and he was a clever man, Le Chatelier's principle is that if you force a change upon a system, so if you force temperature upon a system, it will try to get rid of that temperature or heat somehow. So it shifts in such a way to minimize that change. So it tries to re-establish that equilibrium that was present initially. So find your own definition. If the one you've been taught or the one you have banked in your head is different to this, then take a step back and think, right, is the meaning the same? And if the answer to that is yes, then stick with what you know. Don't learn or don't redesign the wheel for the sake of redesigning it, okay? If it ain't broke, don't fix it. So primarily the three things that will cause the equilibrium to shift is pressure, concentration, temperature, okay? So I'm going to take them briefly, if I just quickly look at the time, yeah, if I take them and separate them into the 3 sections there and discuss with you why it affects it. Isn't the first one then? Concentration, okay, so concentration means how much of a substance is present. So if we change the concentration of any reagent, for example, A, according to Le Chatelier and his principle, the positional equilibrium will automatically move to try and get rid of that additional A you've provided. Well, because A is a reagent, blissfully for industry, if this was an actual reaction, what will happen then is that it will shift to the right-hand side. So it will prioritize that direction of reaction, okay, in order to use up that excess A that you've added. So if you increase the concentration of A, equilibrium will automatically shift to the right to use up that A, okay. What would happen if you change the conditions by decreasing the concentration of A though? So this is like if you removed some of A. So if you tapped it off, for example. So if you're removing some of that and you're therefore denying some of that concentration in the system, that system goes, do you know what? Where's all my A gone? And what it will do, it will try making more of it by reversing the reaction. Okay, so reducing the concentration makes the equilibrium shift in the left direction to try and make more of it. Because if you've taken some of it away, it tries to make more of it. Okay, the same sense, and this is much more common if you remove a product. So this would be classically in the Haber process. So if I just scribble quickly for you, the Haber process that you came across in GCSE. Apologies for that. I don't know why it decided to scribble on my screen, but it did. So if I remind you of the Haber process, this is the equation. Okay, you take nitrogen, you take hydrogen, and you make ammonia. Now that is a relatively unsuccessful reaction, believe it or not. It converts about 10% of the nitrogen and hydrogen into the desired product, which is ammonia. So what they do the clever thing of whatever ammonia is made, they take it and they tap it off. They take it out of the system. As soon as it's made, to stop it reversing itself and unmaking the ammonia, they tap it out. That has a positive effect in the sense that the system then goes, where's all the ammonia gone? It's gone, I need to make more of it. And the equilibrium will then shift in the desired direction most of the time, which is to the right-hand side. Okay. Turning it, in a sense, I suppose, into more of a one-way system, because as soon as you've made the product, you remove it so that you don't unmake it. So pressure, when it comes to Le Chatelier's principle, is only really applicable when everything is in gaseous state. So everything, you're dealing with gases. Now that does in fact apply to the Haber process, because if I go back to the one there for you, all of these are gaseous. So you've got gaseous nitrogen, you've got gaseous hydrogen, and it does make initially gaseous ammonia. Okay, so if you've got all gaseous, it's then probably better to go back to simplistic thinking. And I literally tell my pupils, go back to being a child when the ambition was just to get away from the crowd. So think of it as a crowded room, okay? If you've got the knowledge that each molecule of gas, and this is a fact that probably until later on to GCSE, or not even until year 12 for some of you, you're not aware of, every molecule of every mole of a gas has got equal volume. So it doesn't matter if you've got a mole of hydrogen gas or you've got a mole of carbon dioxide gas. They'd have different masses because they've got different atoms present, but the volume that they would occupy is exactly the same, okay? So carrying that knowledge with you is all about having one side of the equation possibly more crowded than the other one, because each molecule takes place, occupies the same amount of space, okay? So according to Le Chatelier's principle, and remind you again, the position shifts to try and undo or reduce any change you've enforced on it, okay? So if you enforce a high pressure on a system, it tries to undo that pressure by going in whatever direction has the least occupancy or the least crowded side. Okay, so if I take it from this one, it's another generic one, but the specific thing here is that you can see that you've got 3 moles that side and you've got 2 moles that side. Agreed? So when you think about it, if you think of just bare basic occupancy, and let's say 1 mole is 24 decimeters cubed, okay? But if you think of it, keeping the numbers as simple as possible for this evening, if you think about A being 1 square meter and B being 1 square meter, you've got 3 square meters of area on the left-hand side, and then you've got 2 on the other side. So it's like having 300 people in one room, 200 people in the other. You're going to go in the direction where there's less kind of crowding. Okay, so in this case, there are 3 moles on the left, 2 moles on the right. So by forming more C and D, the system causes the pressure to reduce. So if you enforce a high pressure in a system, it is more favourable and more sensible for that system to rush forward in the right-hand direction, because that's the way of reducing the internal pressure that is present. Okay. Decreasing pressure, though, would be the exact opposite. The stoichiometry, or the number of moles that we're concerning ourselves with, hasn't changed massively. Okay, so it's still 3 to 2. So if you decrease the pressure, the system will go, oh, where's all the pressure gone? And it will go in the direction where it wants to increase the pressure again, and that is achieved by going in reverse. Okay, so it can only be made by making more molecules and going backwards. Okay, so there is a kind of rationale of whether or not sometimes you want a pressurized system or you want a low pressurized system. If you have the same number of particles on both sides, then there is no equilibria based argument for having a high pressure or a low pressure. What will contradict that or feed into that decision that's taken is often rates. So even though maybe having a pressurized system doesn't make any more product, it will certainly, according to the laws of rates of reaction, make it in a shorter amount of time. So if you have the same amount on both sides, increasing the pressure has no effect on the position of equilibrium, but it will make the products reach the equilibrium in a shorter amount of time. Okay. Temperature. Now, this is often looked into in grade teaching. It's one of the favoured questions. So it says, if you increase the temperature, what will happen to the yield of one of the products or reagents? Okay. So it matters massively in this case whether the reaction And admittedly, this is something that's touched upon in Unit 2, so it doesn't make massive amounts of sense. But you did do it briefly in Key Stage 4, where you discuss whether reaction is exothermic or endothermic. Okay, so we've gone into energetics, I suppose, now, and I'm sure quite a few of you have either started or certainly touched upon the unit on energetics in Year 12. Okay, you will be covered in one of the later sessions in a few weeks' time by myself. But in GCSE, you certainly were introduced to the word exothermic or endothermic. So if it takes in energy or gives it out. If a reaction is exothermic, it would have a negative delta H value, as seen there. Okay, so you can see here that if the value is negative, okay, it will be exo. So negative is exo, and positive endothermic will mean that the system is endothermic and requires an input of energy into it. Okay, so increase in the temperature then. If a reaction is exothermic, it already has an excess amount of energy. It doesn't particularly want more, okay? Because if it is exothermic, it's already being forced to get rid of some of that excess energy to the environment. That's what causes temperatures to rise, okay? So according to Le Chatelier's principle, you have to then think, if I force a high temperature on this system, will it go in the forward or the reverse reaction? Well, if the forward reaction, if I go back that slide, is overall reaction is exothermic, seen by the fact that it is a minus delta H, then forcing a high temperature on that system will force it or make it go backwards. Because if forward is absorbing the energy, is giving out the energy, then going in reverse will absorb it again. So if you're supplying it with energy in the form of a high temperature, it will favor the reverse reactions, okay? So it's all about trying to have a compromise then, okay? And that's what I will move on to get you to think about, is whether you want to have lots and lots of products, or whether you want less product, but possibly made in a shorter amount of time. Okay, so all these slides, as I said, are available to you. So maybe with a bit of hindsight, you will be able to go back and just absorb it slightly better. But there is a summary, okay, that I've put there. So increase in the temperature in dynamic equilibrium favors the endothermic reaction. That is a kind of clear fact that will not change. Any increase in temperature will automatically shove that equilibrium in the direction of the endothermic one, the plus delta H direction. Okay. Now, this is where it gets a bit confusing, or not confusing them, but it has to, what we call compromise, is that they will often have a reaction that's favoured solely based on equilibria, which we're doing today, that favours a low temperature or a low pressure. But on the other hand, you've got this argument of actually, if you do it at those low temperatures or low pressure, is that the collisions will not take place in a realistic or desirable time frame. Okay, so the rate is increased with increase in concentration and temperature. That's not going to change. That was something you carried through from Year 10 when that unit was done in Year 10 GCSE. Hot temperatures are better. It makes things react faster. Okay. The problem you have is that if a reaction is reversible, making it faster might just well make it go faster in the wrong direction, or the direction you don't want it to go in. Okay, so the rate is increased with concentration or temperature, but often this causes equilibrium to lie in favour of the wrong side. So you often come up like the Haber process. So if I go to the past paper question, you can see there that you've got a reaction that has, and you'll be pleased to know all of these have the mark schemes following them. Okay, so it says there you've got ammonia reacting with oxygen to make nitrogen oxide and water. Okay, it is again exo. Okay, and if you add them up, it's all gaseous. So what we have is a total of 9 this side And if you look at the other side, we've got 10 that side. So there's no massive difference in pressure going to be present here. Okay. But low pressure and low temperature would give the maximum equilibrium, yes or no? Have a think about it. Okay. Low temperature certainly would be favoured because we know that it's exothermic, so lower temperature means that it will favour going forward as opposed to reverse. Okay. However, if you think about it, you're going from 9 to 10, it's a massive shift in pressure by going in the different directions. But certainly low pressure might indeed favour the side which has the lower number of particles. And in this case, that's actually the left-hand side. So low pressure isn't doing the system any favours. Okay. Right. Moving on to the past paper, and I know that the session is quickly drawing to a close time-wise, because I know and I appreciate that you've been with me for a while and you've been in front of the computer for a while. But just to take you through a few other past paper questions, it says there, okay, and this probably I haven't touched upon, and I maybe should have mentioned, it's another kind of mistake when you're dealing with the word catalyst, is that people often say, oh, it makes more product. Be careful, okay? A catalyst will not only catalyze the forward direction, which people are familiar with, but it will also catalyze and make the reverse reaction equally as fast, okay? So it speeds up the direction of both the reactions. So a catalyst doesn't in fact make any more product. And be careful that you avoid that sort of, I would say, sloppy vocabulary. As an examiner, it's something we often see. Is people say it makes more product. It doesn't make more product. It makes the same amount of product, but in a shorter time frame. Okay, and that's what you need to keep focus on, is that you don't throw away little marks here and there by saying something you know is not accurate and no isn't perfectly correct. But if you say it to a normal person, they understand what you mean. And unfortunately, when you come to year 12 and year 13, understanding what you are trying to say isn't going to be sufficient. So there's lots of what we call in year 10 and 11, what we call BOD marks, benefit of doubt, and examiners are a lot more lenient with BOD marks in year 12 and in year 10 and 11. But when you get to year 12 and 13, unfortunately, the examiners are forced to be a bit more strict, a bit more nasty. So you have to be very, very clear. Your answers have to have that clarity to them that doesn't avoid any ambiguous language being used. Okay. Right. I am fully appreciative that it is now 6 o'clock, and you've been with me a while. I haven't got to the end of the PowerPoint, but I in all fairness, was aware that I wouldn't get to the end when I started. Okay, what I wanted to do was give you a resource that you could, at your leisure, then following this session, when this resource is sent out to you, that you can browse at your leisure in your own time, just get a bit of more understanding. And as I said earlier, every past paper question will be followed by the mark scheme, so you can use it as your own revision resource. Look at the PowerPoint, okay, and when you've got the question, you think, right, I think I know the answer, check. Was your understanding correct? So use this resource, use it in whatever way you see fit, okay? But it's all there for you, and the end of it also takes you into the next bit of the topic, which was the equilibrium constant KC. So it's all there for you to browse at your leisure. It's really difficult to condense it into 40 minutes, but I felt it was probably more important for you to get a good understanding of the first two than to get a weaker or less quality understanding of the whole concept. Okay, but I've included the notes for the whole concept in the PowerPoint just so you can kind of browse at your leisure. Okay, so there's lots for you to see afterwards. Now, hopefully that was beneficial for you, and it gave you a bit more of a kind of foundation understanding to what this topic is all about. And hopefully I haven't bored you too much, and you'll be coming back next Thursday to listen to the next section, which actually I'm not sure, Mr. Black, is what was next week? What are we covering next week?
It's periodicity.
Okay, so periodicity.
In the periodic table, yeah, topic 1.6.
Okay.
And just to let you know, you've had some great feedback. Yeah, great lesson. Thank you from one of the attendees.
Okay, well, thank you very much. And hopefully it'll be Mr. Black leading on the session next week, and I'll be answering the questions remotely. But hopefully you'll all tune back in next Thursday. Ta-da!